This talk is like introduction to observability for developers, but I will raise some questions that like pretty interesting in this space. But I am a bit biased because we built an open source observability tool, and we have some our unique approaches, and I will show you this space through my understanding of the problem. Yeah, I will use Coroot as an example of how we look at observability and how we monitor our applications and so on. So let's start from the very beginning. What is observability? Observability, from my perspective, is being able to answer questions about your system. How is the system performing right now? What is its response time? How many requests it processed? Are there any errors? And why some requests perform longer than before? And observability, it's not about storing metrics, traces, and so on. It's about being able to answer questions. And why do we need observability? The first reason is availability, because if we run our applications to earn money, if our application is not available, we can serve our users and we can make any money. So the next one is performance. Like Amazon many years ago posted their research on how application latency impact revenue. So as faster your application serves user requests, then you can expect latency revenue can increase because users are happy and so on. And the last one is cost. If we optimize our applications, if they consume less resources, we will pay less like to our cloud vendor. And it's on some scales, it's super important to continuously optimize your applications. These days, a super common term for observability is pillars of observability. It's all about data. We know that we have logs, metrics, traces, and profiles, and few words about what does it mean. Like, here is my hello world application in Go. It does nothing, just serve some HTTP requests. Which questions we might have to understand how it performs right now. The first one, we need to know how many requests it served. Are there any errors? Per response time or latency? We need to understand like 99 percentile of latency, how we serve the majority of our users, user requests, and about resources. Yeah, we should understand the CPU usage of this particular app, and memory usage and network bandwidth and so on. So let's start from we know nothing about modern observability stacks and tools. The first step, we can add logging into our applications. We can write into some journal, for example, each request. We can add latency timer and write response time for each request. Usually, like when we're talking about logs, it can be split into structured or unstructured. Structured can be parsed, and some metrics can be extracted right from the logs. Usually, each log line and message have some severity, like warning, error, debug. It's like for easy filtering. And we can store logs right on the same node. It's just use plain text file, or we can collect our logs in some centralized storage. But logs, like from developer perspective, it's super easy to add into our application. We can journal anything we want. But in fact, when we deal with some outages and issues, our brain cannot parse and read through many log lines at the same time. It requires some aggregation. Our brain understands charts or some visualization much easier than like hundreds of text lines. And on some scale, it's pretty expensive to store. That's why we have metrics. Metrics, think of it like we have some individual events like requests from user A, requests from user B, and we can log them. But metrics is some aggregation. For example, we took response time of each individual request and calculated average, and just created a time series called request time average, and we can visualize it. And now it's pretty easy to understand what's happening with our application latency. Metrics much more cheaper than logs, easier to understand, but at the same time, doing some aggregation, we lost the ability to understand what's happened with any particular request. We only have some signal or aggregation. And the next observability pillar is traces. Trace is some records with timers, and we can use this information to understand what happened with our particular request from our user with some trace ID, and how this request went through our services. If we use microservice architecture or just a bunch of services and databases, and traces allows us to understand what's happened, the latency of each particular stage of request processing, and so on. That's how typically trace looks like. We have some trace ID. We know that processing started from service called front end, and then we use a bunch of services. We see timing. We can see some name of each stage. For example, we can add spawn for some function call, and it's pretty clear what happened with this particular request. We can also understand the status of each stage and so on. But traces also tracing super expensive on scale, because each individual request can generate us like 100x spawns, and we should store them. We should be able to query them, and it's like can be really expensive, and that's why many observability tools and vendors suggest to store only a fraction of your requests. It's called sampling. But traces allows us to like see all stages of each request, and it's the easier way to answer a question about each particular transaction. And the last one, profiles. Profiles, it's a relatively new telemetry signal, because now we have a lot of instruments that allows us to organize continuous profiling of our infrastructure, where with some frequency we can understand code stack traces executed on each CPU, and we can calculate CPU consumption of any app precise to the code log line. It's pretty useful and allows us to answer about a question about why at this period of time, during this period of time, our application consumed twice more CPU than before. Profiles allows us to answer a question why our application consumed more CPU time, for example, or memory than before. And we can understand the issue precise to the code log line. Here is a typical way how we can represent profiling data. It's a flame graph, and wider areas here means more CPU time spent on the functions. And we can understand that in our case, this function consumed the majority of CPU time. Also, profiles allows us, since we have data about CPU usage at this particular point of time, we can compare some, for example, anomaly with the previous time and understand what's changed. For example, in this case, we highlight with red like the most significant increase in CPU consumption. My co-founder Peter Zaitsev like created a poll in his LinkedIn and about the most usable telemetry signal, and users voted, and the majority of them have chosen metrics. But from my perspective, the right answer, we need all of them, because each telemetry signal has its pros and cons, and there is no silver bullet in this space. For example, traces cannot answer questions about why this service performs slower. We can only see the total latency increase associated with the service. But for example, if we had increased garbage collection time in Java virtual machine, usually you need other metrics or profiles to detect this. Now let's talk about instrumentation, how we can gather all this telemetry data to be able to find answers using it. The first approach is manual instrumentation. We can add to our code some timers. We can integrate some ready-made solutions such as OpenTelemetry. OpenTelemetry is a vendor-neutral SDK for many programming languages. You can integrate your Java applications with OpenTelemetry SDK, and you will have traces covered all the network calls, server calls, and so on. It supports metrics, logs, traces, and now they started to work on continuous profiling. Usually, manual instrumentation requires code changes, but in some cases, it can be just you need to integrate your applications with, for example, Java agent. But still, you need to change your code, redeploy it to production environment, and then you will receive telemetry signals about your application performance. A bit different approach uses some operation system features. For example, eBPF. We at Coroot actively use eBPF to instrument code without the need to change it. It's a feature of the Linux kernel. It allows us to run small programs in the kernel space. The technology guarantees that it will not be a significant impact in your application performance. This approach allows us to instrument even applications you cannot, their code you cannot change. For example, third-party and legacy services. And it's pretty useful, but it should be, someone should implement telemetry sensors, agents to gather together performance metrics using eBPF. The next step, we can work only with application performance metrics or traces or logs, but each application runs on some node. It can be virtual machine, it can be cloud instance, bare metal servers. And to understand, for example, why some applications is experiencing a lack of CPU time right now, you need to understand what's happened on the node. So we need to gather node level telemetry. Also, our applications usually communicate through the network, and we need to understand how our network performs. For example, network latency, packet loss, and some network level errors such as unsuccessful connection attempts and so on. The next part is we not only is responsible for our applications performance, because our application usually work with some databases. It can be managed databases, it can be our self-hosted databases, and we should understand why these databases perform slower than before, or why they fail to execute our requests, queries from our application. So we need to monitor everything around our applications, and that's can be pretty big task to cover all our infrastructure with monitoring. But let's assume we somehow gathered all this telemetry data. What's next? And from my perspective, it's the biggest challenge in this space, because we have a lot of tools that can help us gather telemetry data. We have a lot of databases for storing telemetry data. We even have many UIs for working with our telemetry data, such as Grafana, Datadog, and so on. But to understand what's happening right now in your infrastructure, you should understand how to query this telemetry data, which signal to use first, and how to go through the application stack to find the root cause. And our approach here is that we always start looking at our system from an overview, from big picture, and then if we have some anomalies or errors, we can drill down into our applications, traverse dependency graph, and understand that at the end we can identify the affected service and understand why it performs in different way, like why it serves errors or has increased response time. As an overview, I always suggest to use metrics related to your user experience. If you're talking about web applications, that's the number of errors and latency. That's it, pretty simple. And the traces or metrics based on traces are great here. For example, at Coroot, as an overview, we suggest to use heat map. Here we have a timeline and the number of requests served by our system in each point of time. Also, we have like color and like y-axis here shows reflects our application latency. For example, lower regions means lower latency, and requests here means higher latency. Red areas here means errors. So we can easily understand that here we have pretty good situation. All our requests serves pretty fast, and here with some errors. So we can just select the service and understand what's happened here. So we can allocate the service, in this case, it's service product catalog, and we understand that 100% of this request related to the service. Pretty easy, but the most important point is here is to have some like I call it telling overview, and it's easier to understand. Next, we can also understand that there is some latency anomalies. Request from here went to the higher latency area, and we can select them and understand the services consumed the most of the time. In this case, we was waiting for Redis. And but we cannot with traces in this scenario, we can only understand what something goes wrong, but we cannot answer questions why. And to do so, we need to work with other metrics. And for example, in case of Java, it can be like stop the world pauses in Java virtual machine. If we execute some requests on Postgres, they can be logged by other queries. The traces don't give us such answers, and we need to go deeper and understand what's happening with any particular service. And in this approach, it's really important to have 100% coverage. And for example, in this scenario, using eBPF is super useful because it allows us to, like just by setting up agents on the nodes, allows us to cover all our services. Next, for example, with traces, we identified the problematic service. What's next? So we need to be able to look at any particular service in general and all its subsystems, log, status of each instance, detailed metrics about, for example, runtime, JVM, .NET, and so on. So, the next big picture of our system is the service map. Service map shows us how services communicate with each other and allows us to see, for example, latency between any services, the number of errors, and so on. And we use this service map not only as a visualization of our system, but also we use it to traverse this graph. For example, we see some anomaly here. We can understand that we need to check this service, then front-end service, and all its dependencies. And if we look at any step, we can understand quickly what's happened there. And when we look at any service, we know a lot about them. We know how it performs, who are its clients, who are its dependencies, like databases and other services. We know like the number of instances, where they run, CPU usage, and so on. And also, like when we talking about understanding what we want to know about each service, I usually like many guys told me that it's the infinite number of metrics because not all applications are built the same, and but I suggest to write it down, all possible variants and all possible metrics, and like it's not you I believe all of them will be the same, pretty the same. Like we want to understand how each service performs in terms of latency, errors. We want to understand resource consumption, like CPU, memory, disk, network bandwidth, and so on. We understand runtime parameters, JVM, .NET, Python, global interpreted log, and so on. Ruby, like we want to understand what's happened in each runtime. We want to understand what's happening on the relevant node to like their CPU usage, their network bandwidth, errors on the network interfaces. We want to understand connection latency, TCP connection latency. We want to understand network latency between each particular services. And also, usually problem is related to DNS. We want to track DNS queries by each service, logs and profiles. Like that's it. You can imagine some very specific application parameters, but I believe that 80% of possible root causes can be detected with these metrics and signals. And a few words about how at Coroot we implemented automated analysis of performance of each application. Like our tool is pretty opinionated. We believe that we can provide our user with some predefined inspections, and these inspections can help you identify over 80% of common pitfalls automatically out of the box. So there's the first one, the most important one, is SLO, service level objectives. We define, or out of the box, Coroot has some predefined thresholds. We expect, for example, that each service should serve 99% of requests without errors and 99% of requests faster than 500 milliseconds. And if something goes wrong, Coroot can identify it. And also, alerts are based only on SLOs. So in our product, we notify users only about SLO violations. If your service is meeting its SLOs, you don't need to know about high CPU usage on related nodes or any other problems. Next, we should check the status of each instance. No matter we run our applications on Kubernetes or it's just dedicated servers or virtual machines, we want to know all the instances. We want to know their statuses. Are they available or not? And we should understand the related node of each instance, because when we look at related nodes, we only want to know the relevant nodes. Because, for example, if you run your 3-instance application on a cluster of 1,000 nodes, you don't need to know about all the fleet. Just focus on the related node, and it's super useful. The next is CPU usage. We check CPU usage against CPU limit if defined, if applicable, and we also track CPU usage on the related node. And when we focused on just a subset of our nodes, it's easier to provide users with a single pane of glass. So you don't need to build a mapping in mentally and go through your dashboard tree to locate the relevant nodes. And here you can see everything. For example, in this case, we have service called recommendation. We know the CPU usage of each instance, CPU limit. CPU delay is also pretty useful metrics when we're talking about shared infrastructures like Kubernetes, for example. You can detect whether the instance experienced lack of CPU time or not, without looking at CPU usage and other metrics. Or you can understand that this node is overloaded right now because of other application. The same about memory. Out of the box, we track memory leaks and out of memory events. So about memory, it's pretty useful to know whether your application was terminated by own killer or not, or have some proactive checks detecting memory leaks. And also, if your application were terminated by the own killer, it doesn't always mean that you hit your memory limit. you can have out of memory capacity on the node. And in this case, it's pretty useful to understand the top memory consumers on the related node. The next one, network inspections, is super important because now these days every application is a distributed system. Many services communicate with each other, and with the right metrics and right visualization, you can understand what's happened in your network, even if you run multi-region, multi-availability zone cluster. You can understand what's happened between any particular instances in terms of TCP connections, network latency, and network connectivity. And in Coroot, we implemented out of the box predefined inspections that traces all the network related issues. And in case of DNS, with eBPF, we can capture DNS requests made by each application. And we also can check DNS latency. So we can detect all issues related to this layer pretty easy. And logs. Logs, our agent discovers and gathers logs of each application. And in the single pane of glass, you can see the relevant logs. But I believe that it's not super useful to analyze logs line by line manually. And that's why we implemented repeated patterns extraction from logs. So our agent right on the node turns logs into metrics. So in this case, you can see that we have three error patterns with severity level error and two with severity warning. So it's easy, like, because I've seen many times how engineers work with logs. They just try to find, using command line tools, for example, they can find some patterns, then they use regex to calculate the number of message with this pattern, and that's why we implemented this at the agent side. It like pretty optimized piece of code, so it doesn't consume a lot of CPU time. Next, like runtime specific metrics. Each runtime has like many different parameters, important parameters. For example, Java, in case of Java, everyone knows about garbage collector, and that's why we want to understand the garbage collector activity. And most important parameter is stop the world pauses or GVMSF points. Like we also have predefined inspections for this, and if everything, we can, for example, compare application latency with garbage collector activity and find the correlation and highlight this problem. Next one is like analyzing rollouts on Kubernetes or deployment, because these days each application can be deployed many times a day, and with Coroot we analyze the difference between performance the current release with the previous one, and we can automatically identify performance degradation or increased resource consumption. And even if you run on the cloud, we can recalculate, for example, increased CPU consumptions into money. And yeah, I'm almost finished. So the important part also here is be able to deal with many services at once. That's why in Coroot we invested a lot of time implementing right overview, because here we can have many services and we sorted the application health status by the importance. For example, three applications on top, for example, we can easily see that front end is violating its SLOs, availability SLOs, and has failed connection attempts to its dependencies. We also know that it has three unique error patterns in the logs. So, and this here, with service recommendation, we can see that all of its instances are unavailable now. And for service user, we detected some failed connection attempts to its dependency. So, and having these, we can easily understand the status of our system without the need to check our service one by one. And concerning alerts, I mentioned that we believe that only important thing to be alerted or notified are SLO violations. We implemented Google's best practices in our product. We alert only on significant error budget burn rate. So if we understand that this performance degradation is significant, and only in this way, in this case, we alert our users. We can alert into many notification systems, and also since we know a lot about each application, we can easily attach all our findings into the alert. So you don't need to be notified about high node CPU usage. You will have everything related to this particular app in one alert. And my takeaways from this talk is like we should make our application observable, because if we have to deal with many services, at some point it can be unreal to find the root cause manually, and we should write application logs. We should instrument our applications with OpenTelemetry. We should install something that uses eBPF to gather telemetry data. And as I mentioned, it's not super important where and how you store your telemetry data. Observability is more about extracting answers from this telemetry data. And I believe at Coroot, we help our users to do it pretty efficient. And yeah, we built open source product, and I encourage you to give it a try. It's open source and distributed under pretty permissive Apache 2.0 license. So that's it. Thank you for your attention. If you have any questions, I'm happy to answer.